Okay, now we're going to talk about how to go back and forth between angular variables and linear variables. So I've got another rigid body, it's just spinning. We've got it spinning in a positive direction. And let's say that some point, I don't know, you put a light on it or a bug or something, goes from here and it spins around and it goes to here. Okay, well, you just traversed an angle. So I have a certain, whoops, that's crooked. Let's not make that crooked, please. I'm talking to myself. Okay. Toot, toot, toot. I just traversed this angle, theta, but I also just traversed this linear distance along the arc, which we call the arc length, which is usually described as s. Okay. You're probably wondering why we never use s for anything. Like, why didn't we use s for speed? Well, because s stands for arc length. Okay, so how do we go back and forth between these? How do I find s if I know the angle? Or how do I find the angle if I know s? Well, if this is radius, then the arc length is equal to the angle that you just traversed times the radius. That's it. If you want to go back the other way, you simply solve for theta. So then theta is the arc length divided by r. Now this only works if theta is in radians. You've got to make sure it's in radians. Your calculator, well, we haven't done any sines or cosines, so that wouldn't matter, but calculators in radians, which will be nice because I know some of you were all freaking out last unit because you're in calculus where you use radians all the time, and then you come to my class and the calculator would still be in radians and you try to do my problems, everything would mess up. Anyway, okay. Now, let's say that point was also, oops, wrong page. That point was also, when it did that, it was, well, obviously it was moving. So we had an angular velocity, but is there a linear equivalent? Well, there is. Let's say that point, and I'm just going to use this point right here, it was also trying to move in a line. That line was always changing direction, so the velocity's direction was always changing, but at any given point, so let's say this point right here, the velocity was tangent to the circle. Remember, to make a tangent, the radius and the line should be perpendicular. And I'm a little off, sorry, but just pretend, okay? So, this is how many meters per second the, what do you call it? Oh, I just blanked. Oh, no. That's how many meters per second the dot traverses. And the angular velocity is how many radians per second the dot traverses. So to equate those together is pretty easy. If you think about it, v is like the derivative of s, kind of, like the change of s per unit of time. And if, well, we could go that way, but easier just to tell you, the tangential velocity of the object, so whatever it is going to be equal to the angular velocity times r. You might be starting to notice a pattern here. You just take the angular variable and multiply by r to get the linear variable. Okay, if you wanted to go back the other way, of course, you just solve for omega. Omega is tangential velocity divided by r. Okay, now that v may be changing. Okay, so we could also have a linear acceleration. Let's see, I need a new color. How about this skyish looking blue here? Yeah, okay. This could be changing, so we're going to call that tangential acceleration because we actually have two accelerations here. We've got how v could be changing, so I'm actually going to define that as, oops, wake up. Oh, what happened? That was strange. I had a little glitch. We could define that as when I say tangential acceleration, I mean by this. Well, actually, no. How am I the change of velocity perpendicular to the rate, or yeah. Okay, and that follows the exact same pattern that we've been doing. So that's just going to be the angular acceleration That alpha looks funny. That's better. Times r. But we also have the fact that v is constantly changing direction. That's an acceleration too. So that's going to be, use orange for this, that's going to be an acceleration toward the center. That's centripetal acceleration, or we can also call it acceleration along the radius. Okay, so we can do centripetal acceleration or acceleration in the radial direction. So this is a change of v parallel to radius. Okay, and that, well, we've done centripetal acceleration before, but in what do you call it? Angular stuff, it ends up being angular velocity squared times r. Or if you want it in linear terms, which is what we've done before, it's v squared over r. Okay. I'm out of room, so I don't really want to... Well, this one doesn't have a way to solve backwards. There isn't like an equivalent in the angular direction because angular doesn't move along a radius. It only moves around like this. So there isn't really a thing. However, we could solve this if you wanted to. If you want angular acceleration, you could do tangential acceleration divided by r. Okay. I think that's everything for going back and forth to linear for now. I'm looking, yeah, so that's the end of that one.